Hey everyone, and welcome to this explainer. Today, we're breaking down one of the most elegant and honestly kind of mind-blowing concepts in Class 12 chemistry, the 4 colligative properties of solutions. Whether you're actively reviewing for your finals right now, or you're just trying to wrap your head around exactly how solutions behave, we are going to directly compare the math, the graphs, and the core concepts step by step. By the end of this, you'll see exactly how they all relate to each other.
Okay, let's dive right into this with a little mystery. Why on earth do sugar and urea affect boiling water identically? Seriously, think about it. If you take 1 mole of sucrose, just ordinary table sugar, and dump it into a kilogram of water, the boiling point goes up. Well, if you take 1 mole of urea and do the exact same thing, the boiling point goes up by the exact same amount. Sugar and urea are completely different molecules, right? They have totally different sizes, different shapes, different chemical structures, and yet the water just doesn't care. It treats them exactly the same. Why? Well, that mystery is the very heart of what we're uncovering today.
So, here is our game plan for today. First, we'll answer what are colligative properties. Then, we'll look at the lowering of vapor pressure, compare boiling elevation versus freezing depression, and explore the power of osmotic pressure. After that, we'll hit comparing all 4 properties, and finally, we'll wrap up with the Van Hoff factor.
Okay, Section 1. What are colligative properties? The rule of numbers. Before we get into the math, we really need to define the core principle that unites all 4 of these distinct physical phenomena.
You know, the secret is actually hidden right in the name itself. The word colligative comes from the Latin roots co, meaning together, and ligare, meaning to bind. So these are properties that are bound together by a single inescapable rule. And that rule is they depend entirely on the collective quantity of the solute. It is the ultimate rule of numbers. The actual identity of the solute, whether it's sugar, urea, or some giant complex polymer, is completely irrelevant. The only thing that dictates the change in the solvent's properties is the ratio of the number of solute particles to the total number of particles in that solution. Actually, scratch that. It's more like a pure numbers game. Nothing else matters.
Moving on to Section 2. Lowering of vapor pressure. The first domino. Now that we know it's a numbers game, let's look at the foundational phenomenon that triggers everything else.
All right, here's the core phenomenon that you absolutely need to cement in your mind. When you take a pure, volatile solvent, like water, it has a certain vapor pressure. But the moment you add a non-volatile solute, something that doesn't easily turn into a gas, the vapor pressure of that solvent instantly drops. Why? Well, it's pretty intuitive. Those solute particles take up space at the surface of the liquid, literally physically blocking the solvent molecules from escaping into the gas phase. It's like a microscopic traffic jam at the surface. And this simple drop in vapor pressure is the singular domino that knocks over everything else we're about to see.
So the crucial point is how we actually measure this drop. This brings us to a really specific form of Raoult's law, and honestly, the math here is beautiful in its simplicity. The relative lowering of the vapor pressure, which is just the change in pressure divided by the original pure solvent's pressure, is exactly equal to the mole fraction of the solute. Notice the variable I just said. Mole fraction. You're going to want to keep a close eye on this because comparing which concentration variable is used for which property is an absolute must for Class 12 exams. This mole fraction perfectly aligns with our definition of a colligative property. It's a direct ratio of the solute particles to the total particles.
Section 3. Boiling elevation versus freezing depression. Temperature limits. Because that vapor pressure has been lowered, the temperature boundaries of our liquid are fundamentally stretched out. Let's look at how this plays out visually. Notice how on this vapor pressure curve, for a liquid to actually boil, its vapor pressure must rise until it equals the atmospheric pressure, say 1.013 bar. The top curve here is pure water, boiling nicely at exactly 373.15 Kelvin. But for our solution right below it, because the non-volatile solute lowered the initial vapor pressure, the entire curve is shifted down. So to force that lower curve up to the 1.013 bar finish line, we have to pump in way more heat. The solution literally must reach a higher temperature to boil. That gap you see on the x-axis, that is your boiling point elevation, delta TB.
Now let's see how this builds into our equations. On the left, we've got the boiling point elevation formula, delta TB equals KB times M. And on the right, the exact mirror image, freezing point depression, delta TF equals KF times M. The exact same vapor pressure drop that forces the boiling point up also forces the freezing point down. But notice what these two have in common. They are strikingly similar, and they both rely on a completely different concentration variable than our previous property. They don't use mole fraction, they both heavily rely on M, which stands for molality. Remember, that's the moles of solute per kilogram of solvent.
And looking at the constants in those equations, Kb, the ebullioscopic constant, and Kf, the cryoscopic constant, if we compare these head-to-head, you'll see they share the exact same units, Kelvin kilograms per mole. But here is the most vital thing to remember for your exams. Both of these constants depend entirely on the nature of the solvent, not the solute. Whether you dissolve sugar or urea in water, water's Kb is always 0.52 and its Kf is always 1.86. Basically, the solvent dictates the rules of the playground.
Okay, Section 4. The power of osmotic pressure, physical force. We're shifting gears now from temperature changes to a purely physical force across a barrier. Picture a semi-permeable membrane. It's basically a barrier with microscopic holes that only lets the tiny solvent molecules through, but completely blocks the larger solute molecules. The solvent will naturally flow from a lower concentration area into a higher concentration area to try and dilute it, right? We call this osmosis. But if you push down on the concentrated side with enough mechanical pressure, you can stop that flow entirely. That exact stopping force is the osmotic pressure. And here's the formula. P equals CRT. R is the gas constant, T is temperature, but C is the real star here. Unlike boiling or freezing, which use molality, notice that osmotic pressure shifts gears and relies on molarity, capital M, moles of solute per liter of solution.
Now, what's really fascinating is that osmotic pressure actually dictates survival in the real world. For example, if you get an IV at the hospital, the saline solution must be exactly 0.9% sodium chloride, so it's isotonic with your blood plasma, meaning your blood cells won't explode or shrivel up. Or think about history. People preserved meat with salt for centuries. It's basically chemical warfare. If a bacterium lands on salted meat, osmosis violently draws the water out of the bacterium's lower concentration cells and into the salty exterior, causing it to shrivel and die. And on a slightly nicer note, this exact same osmotic pressure is how a giant tree manages to pull water from the soil all the way up into its roots.
Section 5. Comparing all four properties, the master summary. We have covered all four mechanisms. Now, let's bring all the pieces of the puzzle together.
Here it is, your master's summary table. This direct comparison is exactly how you decode Class 12 chemistry problems. Notice the distinct progression of the concentration variables across the four rules. For the relative lowering of vapor pressure, your key variable is mole fraction. For both boiling elevation and freezing depression, the key variable shifts to molality. And finally, for osmotic pressure, we use molarity. By directly comparing these formulas side by side, you can immediately identify which concentration unit you need to calculate first, based on whichever property you're testing. Take a mental snapshot of this.
So you've memorized the rules, you understand the math, but just when you think you have it all figured out, we hit Section 6, the Van't Hoff factor, the plot twist.
Everything we just learned was based on one massive assumption, that one molecule of solute stays as exactly one particle in the solution. But what if it doesn't? What if you drop salt, like potassium chloride, into water and it splits apart into a potassium ion and a chloride ion? Suddenly, 1 mole of solute just became 2 moles of particles. Or what if you have a weak electrolyte, like acetic acid, that partially associates, where molecules actually join together? They just don't play by the basic rules because they alter the actual number of particles. And remember our cardinal rule from the beginning? Colligative properties only care about the final number of particles.
So, to fix this mathematical crisis, we introduce the Van't Hoff factor, represented by the lowercase letter I. This factor corrects the math when solutes exhibit abnormal colligative properties. Think of it as a simple multiplier. If your solute molecules pair up and associate in the solvent, you have fewer particles than expected, so I is less than 1. If your solute breaks apart and dissociates into ions, you have way more particles, so I is greater than 1. You take this Van't Hoff factor and simply multiply it into every single formula we've discussed today to account for the real, actual number of particles floating around in that beaker.
So let me leave you with this final thought. Go back in your mind to that master comparison table we just looked at. If you were handed a highly disassociating salt on a test, instead of simple, boring sugar, how exactly does factor I change every formula you learned? Visualizing exactly where that I plugs into Raoult's law, the boiling and freezing equations, and osmotic pressure, that is the final key to truly mastering colligative properties. Thank you so much for joining me on this explainer, and I'll catch you next time.